In this video, we're going to go over the AP Calculus AB FRQ number 2 from 2008. So in this problem, we're given a table of values where T is in hours and L of T is in people. And this represents the number of people waiting in line to purchase tickets at a given time T. Part A, use the data in the table to estimate the rate at which people waiting in line was changing. So estimate a rate of change at this particular time. So because this is the number of people and we want the rate of change of that, it's just people over hours. And so whenever we're asked to do this, we're thinking about just the slope. So for part A, and I can pick any time interval here that includes 5.5. The most logical one to do is from 4 to 7, but you don't have to do that one. So it's 150 minus 126 over 7 minus 4. And if I simplify that, I get 8. And it wants to show the computations, which we've done, and the units. And that would be people per hour. Part B then wants a trapezoidal sum with 3 subintervals to estimate the average number of people waiting in line during the first 4 hours. So here we're looking for the average number of people. So in general, what I want is for the first 4 hours, so that's the average value of this function from 0 to 4 of L of t dt. It's just that I don't have an equation for L of t, so this integral portion has to be done by some sort of sum, and in this case they want a trapezoidal sum. So if I look at, say, the first 4 hours here, I'm just going to use break this into equal chunks from 0 to 1, or sorry, not equal chunks, but the 3 chunks given to me: 0 to 1, 1 to 3, 3 to 4. So here we go. So I'm going to leave this 1/4 on the outside, and then for each of my trapezoids, I've got 1/2 base 1, which for the first one is 120. Plus base 2, which is 156, times the width here is 1, plus 1/2, base 1 is now 156, plus base 2 is 176. Now the width from 1 to 3 is 2, and then last one, see if I can squeeze it in here. Base 1 is 176, base 2 is 126, and then that's times 1 because we're going from 3 to 4. There we go. And if the trapezoids are weird for you, just think about each of those trapezoids. If I were to draw the first one, here's one. It's going to have a height of 120 for the first edge, and then a height of 156 for the second. But in a trapezoid, those are the bases because the height is this part that's parallel between the two bases. Or, I'm sorry, the height is perpendicular between the two parallel bases. All right. And then you don't have to simplify that at all, so I'm not going to. But certainly you could. It wouldn't be wrong to simplify that. Stop it. No. All right. So that's A and B. For C, what is the fewest times in the interval from 0 to 9 at which the derivative must equal 0? Give a reason. Okay. I'm going to go ahead and get rid of all this work for A and B, so go ahead and pause and write any of that down if you still need to. All right, so as I look at the values here in my table, I can see that we go from 120 to 156 to 176, that's increasing. Then we dip down to 126, then back up to 150, then down to 80, then still down to 0. So my graph, just a very rough estimate, and I don't know for sure, but based on the graph, it looks like we're increasing until we get to 3, and then we decrease until we get to 4, increase again until 7, and then decrease all the way until we get 0 at 9. Now, this is just based on these values in the table. Now, it is absolutely possible that we had like a crazy dip over here, and that maybe we had a dip and a jump and a dip here, and then maybe we were way up here and then down and all this crazy stuff. But in order to answer the question, because the question says, what is the fewest number of times? I'm going to get rid of all those extra bumps that could be there and just go with the ones that I know are there. All these extra bumps, I don't know for sure. But these ones have to be there because I have to increase from 120 to 176. I have to decrease from 176 to 126. I have to increase again to 150 and then decrease. So I have these relative maximums and minimums here. Now it's definitely possible in a general graph that I don't have a nice smooth curve here, and obviously my stylus draws it very bumpy, but you get the idea. It's possible that I have a sharp point, a cusp here, or maybe we just jump, right? Maybe we have a piecewise linear function that is just jumping all over the place here, and the derivative is never actually 0. Well, that's not allowed because our function is said to be twice differentiable. So we know, I think that for me, the easiest way to explain this, not the only way, but the easiest way for me is to say, because L of t is differentiable, and changes from increasing to decreasing twice, and from decreasing to increasing once, L prime equals 0, slide it up a little bit here, at least 3 times. Okay. All right, so that's part C. Once again, I'm going to clear this out of the way so that I have room for part D. Go ahead and pause, write it down if you need to. So last part, part D, we're given this equation. Let me slide it back down for us here. We're given this equation that models the rate at which tickets were sold in terms of tickets per hour. Based on this model, how many tickets were sold by 3 p.m.? Which is t equals 3. So if we're given the rate at which something happens and we want to know like the total aggregation of that thing, we integrate. I mean, that's what an integral is. It's integrating all those different things. So given the rate of change of ticket sales, if I want the total number of ticket sales, I just integrate. So the integral from 0 to 3 of r of t dt, which is about 972.784 They want that rounded to the nearest whole number. So we're going to say 973. And they don't want any justification or anything, so that's it. All right, all done.